Good day, I'm Dr. T and welcome to my office. So today I am playing Banished, a game where you and several of your friends are banished from your homeland and have to make a life in the wilderness and set up a community. It's set in medieval Europe or so. Okay, so I've got the game going, and what I need to do is build a couple more houses because I got a nice influx of nomads a little while ago, and, well, they need a place to live. Okay, so I'm going to go ahead, probably build a couple more houses. Not entirely sure where I want to put them, but I can probably use one or two up here. And one of the things I want to look at is when I build the house is actually, well, what is it built from? So once I open this up, I get kind of 5 items that I have to do in the menu. Remove, and that's as if there's anything on the land that has to go away. Trees, rocks, whatever. So that has to go first. And then I'm going to need materials to build my house from. And those are going to be wood, stone, iron, and then my builders have to swing by and actually build the aforementioned house. Otherwise, it's just a pile of rocks, logs, and iron. But as a chemist, I'm actually kind of drawn to those middle 3 and this idea of, well, okay, well, what am I building my house of really? What are those 3 components really like? And those actually highlight some of the fundamental building blocks of how chemistry works and how materials are put together. So let's start with the stone. And the stone actually is going to be a blend of 2 different ways of putting it together. Because stone is not one thing. You have all kinds of minerals. And minerals are different chemicals, so they're arranged differently. So there's kind of 2 main ways that stone's going to be put together, 2 types of minerals that you can start thinking about. The first are going to be ionic compounds. So ionic compounds, you're going to have, some of your atoms are going to be what we call cations. They have a deficit of electrons, so they have a positive charge. I know, you go down and you go up. It's the way we define electrons because they're negatively charged. You reduce the number of them, you get positive. It's annoying. And then there will be other atoms that will have a negative charge, and that's because they have a surplus of electrons. It's not necessarily the case that the electrons came from one, moved to the other. That's kind of a myth that textbooks put in. Quite often, those electrons, that exchange happened with some other atom long, long ago. Although nothing says it didn't actually, although they could actually occur between those 2 actual atoms. So now I've got my 2 atoms. They're differently charged, and so their opposite charges are going to attract. Now, a rock is not made from 2 atoms. It is made from quintillions upon quintillions of atoms. We use moles, 6.022 times 10 to the 23rd, because that's the scale in which we are dealing with the number of atoms, because they're tiny little things. So, of course, you've got multiple atoms, and so they'll be arranged, and what they'll do is they'll arrange themselves in a 3D pattern, where the positively charged ones will be surrounded by negatively charged, and the negatively charged will be surrounded by positively charged, and they'll all be mixed in together, but typically in a very regular repeating pattern, which is what we call a lattice. And something that has a lattice structure, we call that a crystal. So a lattice is the pattern, whereas the actual thing you make with a lattice is called a crystal. So yeah, that was what we would call an ionic compound. Now, it's possible your cations could have, 1 less electron, your anions could have 1 more electron, and thus, you'd have a 1-to-1 ratio, but you also see cases where the cations are short 3 electrons, the anions only have 1 surplus electron, so there's 3 times as many anions as there are cations. That totally happens as well. Just depends on what you've got building your material. And that's going to affect the lattice structure. The size of the cations, the size of the anions, what the ratio is, that's all going to affect exactly what kind of 3-dimensional structure you get. Now, a lot of your minerals are also going to do what's called a covalent network solid. And this is a really weird one. And these are going to be especially things like quartz. So, they got the stuff needed for the house, so I've got my foundations laid. That's always good. Probably should lay another house while I talk. So, covalent network solids are going to be a slightly different story. So with these, you have atoms, but instead of some of them being short an electron and some of them being surplus an electron, they're going to have basically the right number of electrons. So same number of electrons as they have protons. So we call these atoms, not in the previous case where we called them ions. And so in these covalent network solids, you still quite often get that kind of lattice structure, but instead of individuals being attracted to each other due to the positive and negative charges, instead they are sharing the electrons. So I might have a silicon atom and an oxygen atom right next to each other, and they have a pair of electrons, so 2 electrons. Electrons are usually paired. And they'll have a pair of electrons that are interacting with both silicon and oxygen atoms. And as such, they're shared, and that sharing is what we call a covalent bond. And it's called a covalent network solid because that silicon atom might very well be sharing electrons with 2, 3, 4 other oxygens, and each oxygen is probably sharing with 2 silicons potentially. And so you get this whole big 3-dimensional web, which if it's a very ordered repeating structure, we'll call that a lattice and we'll call that a crystal. If it's not an ordered structure, it's just kind of a mess of a web, we call that amorphous. So if you look at like glass, glass is an amorphous solid. It's not a liquid, it doesn't flow. That's a myth that comes to the way glass blowers used to work. And there's no glass blowers in this game. Oh, I wish there's, no I don't. That would make it harder. But that's mostly just an artifact of how glass was blown in the old days. It looks like it flowed, it didn't. But once glass is solid, it's cooled down enough that it's nice amorphous solid. It's not flowing anymore. Okay, that was enough on glass. Let's get back to where I was. So crystalline solids, like a nice diamond, you've got carbons. Each carbon is sharing electrons with 4 other carbons, and you've got this nice, very repeating crystalline pattern. In cases like glass, you've got silicons and oxygens sharing electrons, but there's no 3-dimensional pattern to where the atoms are placed, or at least not a particularly repeating one. And so your minerals are going to have both ionic compounds and these lattice compounds, or I should say these covalent network solids, because you could have things like obsidian, which is a volcanic glass. And these are going to have some rather interesting properties. If you take an ionic compound, those ionic interactions add up quick. And that 3-dimensional pattern with everyone locking in next to each other, it makes it really hard to break those. So ionic compounds quite often are hard to break, but once you distort the lattice just enough, they tend to just snap. Because now all of a sudden it's going cation meets cation and they push apart. What was attracting now repels. So typically, stones aren't going to be very malleable. They're not going to bend or flex. They're just going to break. And hey, you can do that. You can whack one stone on another and they break. Depending on the crystal structure, some stones will break in nice, clean, smooth, predictable patterns, like flint. And thus you can use that to make stone tools. Yay. Other stones don't do that. It depends on both the atomic level, and then it's not uniform. It's not one gigantic crystalline structure. Those are very, very rare. Very pretty when they exist, but very rare. Now, because of this, you also are looking at being able to pack your atoms in very tightly. There's no real gaps between your atoms. There's small gaps, but not much. Also, these typically are going to be higher molecular weight atoms that are going to form your ionic compounds. All your transition metals are going to do this. So this means you can cram a lot of matter into a very small area, and lo and behold, stones are heavy. They're a very dense material, and that's because you've got a lot of matter packed in because it packs very, very efficiently. So the poor people down at my quarry, they're picking up rocks, and it's going to be heavy for them. And so those are going to be heavy. That would be backbreaking work. And in the game, these guys and the guys mining, well, I should say the folks, because the game doesn't do gender distinction in roles like medieval Europe did. These folks tend to die a lot. So this is not healthy for my population, but I need the rock, I need the mineral. And, some people do jobs that are not ideal, and it's not ideal, but sometimes jobs have to get done. Hopefully we pay them properly. We usually don't, but hopefully we do. Okay, back to the chemistry. So you've got your stone. Now, the next type of building material that my houses are built from is going to be iron. And I know, I'm skipping logs. I'm putting logs at the end because I want to talk about my coats when I talk about logs. Okay, so I've got iron. Iron is going to be a metal. Of course, you knew that. So in metals, you have typically atoms that are going to be in the left two-thirds of the periodic table. These will typically do a lattice structure, but they don't do cations and anions. Metals don't typically like to do anions. They like to do cations. So when you get a metallic bond, where you've got a bunch of metal atoms together, typically what's going to happen is they're going to share some of their electrons with the group. Now, not every single atom will be sharing even any of its electrons. Most of them will share maybe one or two. They're not going to share all of them by any means, and a lot of the atoms won't share any, but they'll just kind of, oh, I got my atoms, and we're kind of sharing some of the other ones. Oh, now I'll put a couple of my atoms out in the fray. Kind of like close friend groups taking care of kids, you know. One person's taking care of a couple of kids, and then, you know, the kids kind of bounce around within the friend group. And it's a very healthy way of taking care of kids. But anyways, so we've got the electrons. They bounce around through these atoms. They're kind of shared with the group. This has a couple of consequences. You can bend and flex metals because while you're distorting the lattice structure, you're not switching it to the point where you're snapping shared relationship. It's not discrete shared relationships. These electrons are being held communally, what we call an electron sea. So you haven't broken up the community, you've just changed some of the relationships. And it's not like an ionic compound where you've got positive and negative, and now you've just lined up positive on positive, negative on negative, and all of a sudden the attraction became repulsion. So metals tend to flex and bend. That's one of the beauties of metals. But you can still pack a lot of things in there, so they're typically very dense. And if you try and pull those bonds apart, well, there's a lot of electrons being shared by a lot of individuals. So metals are going to be able to take a lot of stress and really be able to take a lot of force. So that's your metallic bond. Absolutely wonderful materials to work with. Now, let's move on to the logs, the last one. And the logs are going to be a somewhat different story. Logs are predominantly, well, I mean, they're wood, and wood is predominantly made up of two types of polymers. And polymers are going to be these covalent molecules. So these are going to be like the covalent network solids, except for there's no real network going on. So in a polymer, you have small parts, what we call monomers. And these small parts are their discrete molecules. So they're, you know, in the case of cellulose, they're going to be glucose monomers. So you've got 6 carbons, what will start out as 12 hydrogens, but 2 of them are going to get lost in the polymerization process, and 6 oxygens, one of which is going to go away when it polymerizes. But you get these discrete, what we call small molecules. These are things that have a reasonably small number of atoms in them. They're their own discrete packet, so that, you know, these float together as one thing. Think like a nuclear family. So in a polymer, you're going to take these small molecules, what we call the monomer, mono means one, poly means many, and you're going to connect them. And when you connect them, then you're going to take these small building blocks and you're going to create a structure out of them. So this is kind of like those covalent network solids, except for the repeating pattern's not on the atom level, it's on this kind of small monomer level. So it's kind of a larger repeating. And typically polymers don't form complicated networks. They can, but they typically are more either linear or branched in nature. So they're a much simpler three-dimensional structure quite often. So wood is made up of 2 predominant polymers. First is cellulose, and cellulose is made up of glucose monomers. They're stretched, and if you look at a tree, oh look, I've got a bunch of trees, and if I was to look at the tree going up and down, the cellulose chains typically run up and down the tree. And that's why if I've got somebody cutting a tree down, I don't think I do actually. No, I don't see anyone working on trees. But, well, that's too high up. But it's a lot of work where if I go to one of my one of my woodcutters, they're able to take their maul. You don't use an axe per se. You can, but you don't. You typically use a maul, which is kind of a hybrid between an axe and a sledgehammer. And, oh, is she going to do it? I think it's a lady. I can't tell. Yep, that's a lady. Oh, wrong button. Okay, so, wow, the graphics are simplified, but still, she's pounding down on the log. So in reality, a log would be on that stump, and then she's splitting it. Well, to split it, she's splitting apart the cellulose strands. And as the cellulose peels apart, you're not breaking the covalent bonds in the cellulose. You're simply unzipping two different cellulose molecules apart. They're held together by what we call intermolecular forces. And these are much weaker than those shared electron covalent bonds. So it's a lot easier. And so if you look at, these logs, presumably you take a log, you can see them kind of over here, and she's going to hit one of those logs, and then in one stroke, maybe two, she's going to go all the way through that log. But if you go over to someone chopping wood, I'm kind of forced to... Is anyone chopping wood? He might be. So if you've got somebody chopping wood, I'm going to speed the time up a little bit. Well, anyways, I tried to do that. If you're chopping a tree down, you're going to take your axe, you're going to hit it horizontally, and you're going to take a tiny chunk of tree out. And you're going to spend a lot of work going through that tree. Okay, so if you're going through a tree, you're going to take a tiny amount out with a very sharp axe, and you're going to have to, chop through it a lot. Obviously, the direction of swing matters a lot. Gravity helps. But the ability to go through those intermolecular forces is much easier than to go through the covalent bonds. And that is my garbage truck. Okay. Now, logs are heavy, but they're not as heavy as stone or iron because, frankly, they have a lower density. While the tree is growing, it has holes. It has gaps. It's not solid, densely packed materials, and polymers don't usually pack in as tightly as your covalent network solids or your ionic compounds or your metals. Now, as I mentioned earlier, logs or wood in general is going to have a second polymer. That's called lignin. This is a very complicated, really random polymer. It's got lots of carbon and hydrogen in it, not too much oxygen. And this is going to do what's called cross-linking. So as I mentioned repeatedly, the trees have the cellulose running up and down the tree. Now, to hold those together, you've got intermolecular forces, but those are actually fairly weak. So what the tree will do is it adds another polymer that hooks the polymers together. This is what we call cross-linking. Cross-linking is when you take two strands of polymer and link those together. And by doing so, it's more than just intermolecular forces holding them together. You actually have covalent bonds holding them in place. And trees will have lignin, and lignin does this job. Some trees have a little bit of lignin. These are woods that don't usually have a lot of strength to them. Other trees have a lot of lignin, and these are going to be really tough, hardy woods. And, hey, that's an easy way that trees can distinguish themselves. Different type of wood for a different type of tree. Different goals have different needs. So, yeah. We've got our logs. Now, I mentioned briefly that I wanted to touch in on my coats. Where is my tailor? So my tailor is making coats, and I'm making warm coats, which are a cross between leather and wool. So I guess it's a leather outside and a wool liner, which would make a nice coat. Leather and wool are both polymers, or both constructed from polymers. Wool, you have a protein polymer that comes, from the sheep. It's the hair. I believe it's keratin. And so you're going to have a series of proteins, and proteins have, instead of these small carbon, hydrogen, oxygen monomers, they're going to have amino acids, which are carbon, hydrogen, oxygen, and nitrogen. And then wool will also have lots of sulfur-containing amino acids, which act as the cross-linker. That's why when you catch your hair on fire, which I strongly don't recommend doing it, it smells like kind of a rotting egg. It smells like kind of this rotting egg. It has this really distinctive smell to it. That's not particularly pleasant. That's because the sulfur that's being released while it's combusting. The leather, same story. That's a protein, same basic one. That one's going to be predominantly collagen, which is, once again, another protein. And thus, a lot of what we use to build our stuff are going to be these polymers, especially nowadays. Well, not especially nowadays. Even at this point, we were using natural polymers, and in modern day, we're using a lot of synthetic polymers, which are chemically typically simpler, but a little bit more work than just growing a sheep to make them. But you can make a ton of it very easily. So it's kind of the work cancels itself out. So yeah, that's a tour of building materials in Banished. Hope you enjoyed that and have a wonderful day.